Thank you very much. Thank you everybody for being here. So my name is Andrea Isella from Rice University, and I'm tag team with Zhaohuan to present our summary for chapter 12. We are talking on behalf of the other co-authors, starting with Jeong-Eun Lee, which is here in the audience, and Satoshi Okuzumi, which is also here. Scott Suriano, Rebecca Martin, unfortunately they couldn't make it, but please talk to any of us if you have a question that we cannot address during this talk. So our chapter is about trying to summarize the many observations and theory about structure in disks. And I want to start just by reminding you where we were during PP6, and that at that time, ALMA long baseline was still not available. However, ALMA was already observing disk and was already delivering some observation of structure in disk. Structure in disk were not discovered by ALMA. We knew already, particularly for a specific class, which are the transitional disks, that are this class that lack infrared access, and that was already modeled as a lack of dust close to the star. And this disk indeed show cavities already in previous observation, obtained, for example, with starting from Plateau de Bourg observation, SMA, and Karma, and these are just some examples. And that was the state of the art at the time of Protostar and Planet 6. So at that time, if you look at classical disks that were not transitional, they look like this. And this is a very famous example. You all know. I cannot avoid mentioning, obviously, HL tau. These are Karma observations that already achieved pretty high angular resolution in dust continuum, 0.1 arcsecond roughly, and the disk looks pretty smooth, with no structure. We all know that when ALMA observed HL tau is the brightest disk in the sky, and it was the obvious target to test the long baseline. So we got this image, this beautiful image with many rings. And that was really a surprise to some extent. We were thinking about structure, obviously, but we didn't think about finding so much richness in structure in these disks. So this business about studying substructure at high resolution is relatively new. And so the point of our chapter is trying to make a summary. But because it's a new field, don't expect many answers to your questions. So we'll see where we are at the end with that. So this brings me to a brief outline. So I'm going to go through a very brief introduction just to mention how we observe structure in disks, and then our result about statistical analysis of available data about the occurrence and classification of this subtraction. Then I'll pass my microphone to Zhaohuan as a theoretician. He will talk about physical processes and comparison with observation. And then we'll come back together to talk about future prospects and our conclusion. OK, so I want to start to the very beginning. And I know there are many students in the audience. So, but we all know that protoplanetary disks, as pretty much any other object in the universe, they are mostly made of hydrogen and helium. And molecules and the beautiful chemistry we saw, for example, this is we are talking about a teeny tiny fraction of disks. And refractory material like dust particles also make a small fraction that is between, let's say, 1 and 10% of the disk mass. However, when you want to observe disk, hydrogen and helium are pretty much invisible or very hard to detect. And so we have to rely on observation of this rare component. And if you're talking about observing disk at very high angular resolution, due to the limited sensitivity of current instrumentation, we are really limited about mostly looking at dust. Because we can use, for example, the broadband given by ALMA and to beat down the noise, and we can achieve high signal-to-noise images. When you look for molecular line, because you are intrinsically constrained by observing in a very narrow range of wavelength, because your lines are narrow, we don't have the same advantage that we have in the continuum. So in our chapter, we mostly focus on dust emission, although we touch a little bit on gas, structuring gas as well. OK, dust emission can be observed across a wide range of the electromagnetic spectrum, from optical infrared to radio. But you have to be aware that when you pick a wavelength, you see different layers in the disk, particularly in the optical near infrared. What you are looking at is scattered light, is starred light that is scattered from the surface of the disk, is very optically thick. The structure you see, this is a beautiful image of IM loopy obtained with sphere. and where you can really appreciate the fact that the disks are flaring. And the structure that you see are not really density structure. These are structure, first of all, for example, in the scattering phase function, one side is brighter than the other because these small grain mostly have, characterized by forward scattering. And you see smaller scale structure. They might reveal the fact that the surface of the disk is not flat. There might be waves or up and downs. And so scattered light you can see shadowing. So in scattered light, you are really tracing some of the properties in the surface. If you want to understand the structure in the density, you need to get to optically thin tracer. So you need to go to longer wavelength. And that's where really ALMA is playing a major role here. And so here in the millimeter continuum, you start to see the midplane, although the optical depth is a challenge, and we'll talk about that later. And in the, see if we can move on. So in the last several years, we have seen many observations of disk at higher angular resolution in continuum with ALMA. Here I'm only quoting the largest survey, although we are still talking about a small number of objects, the SHARP, and Odysseia, and a beautiful collage made by Nienke van der Marel. And you see there is we're starting to get like a galactic field where you see a lot of galaxies with structure. Now we see a lot of disks with very different structures. So this observation raised several questions, and we are trying to address three mostly. Are disk structure ubiquitous? Do the occurrence and morphology of this structure constrain information processes? So what do we learn about the physics? And what is the connection between this structure and planet formation? What is the connection? Are these structures created by planets? These structures create planets? And that's still a very important question. OK, so to address the occurrence, we try to collect what has been done in the literature up to 2021/2022. And so we put together this catalog of about 500 young stellar objects and in nearby star forming region. And these are objects with no stellar properties, meaning that we know what is the mass of the star. 355 of these have measured millimeter fluxes and density, and most importantly, disk radii. And 73 of these objects have structure, vaguely defined in a way that we'll touch upon in 1 second. So the occurrence rate of structure is about 50%, but only for disk masses, for disks that have masses larger than about 1% of the solar mass. So we can plot this, our finding in this plot, which is a bit complicated, so let me explain it to you. On the x-axis, you have the disk mass, which is inferred, as we usually do, from millimeter fluxes, assuming optically thin emission. On the y-axis, you have stellar masses. And no, there is a non-correlation between the disk mass and the stellar mass, so that higher masses tend to have more massive disk. Is a very loose correlation with a large scatter. There is, however, another important correlation, which is a correlation between the size of the disk and the millimeter flux, so that the brightest disks tend to be the largest. So these points here are coded in the way that crosses are disks with no structures, circles are disks with structures, and they are also color-coded based on how well we resolve the disk. So for example, the green dots are disks where we have 10 resolution elements across the disk. So obviously, to see structure, you need to resolve the emission. However, because there is a correlation between the disk flux and the radius, the brightest disks, that are those that tend to be found around more massive stars, tend to be the largest. And so we obviously focus our attention on these big disks, right? So what you find here in this histogram of the top and the bottom, again, is a kind of, these are distribution. The point is that when you look at these most massive disks, they all have structures. But the observation becomes very incomplete very quickly, because when you go to the lower mass disk, they are small. We didn't resolve them properly or resolve them at all. So we just don't know if they have structure or not. This is very important, because if you think about connecting theory, if you think about general theoretical processes, physical processes that explain structure, you have to be careful about, so are these really general, or are we talking about really a subset of disks? That might be weird disks, because these massive disks are the tail, the population of the disk mass population. Okay, so there is this important observational bias. With that out of the way, there is another problem, how you classify structure, right? Because they are all different. So no, we like to classify things because make our life easier, but a lot of these structures don't really fall in any class. Anyway, so we classify structure in rings, 62 disks out of these 73 have rings. Rings meaning they're circular rings, they appear elliptical because they are inclined. 22 disks have spiral, 13 disks have crescent, 19 disks have more than one structure. And as you can see, structures are observed in millimeter continuum, near infrared, and in some cases in CO gas, although we cannot achieve the same angular resolution in molecular line as in continuum for the reason that I explained before. There are also interesting things. For example, if you look for spiral and crescent, they seem to coexist. So these are 9 objects, and they tend to be massive stars because the reason I told you before, we tend to look at massive stars because they have large disk, where you see crescent in the millimeter wave, but you see spiral in the near infrared. So I don't know we understand this, right? But there seems to be, depending on what layer you see, you may see different structures. Okay, so we went a bit more in detail now that we have this kind of rough classification, we can try to get some statistic. So rings are observed in 62 disks. There are multiple ring systems. We have a total of 120 unique rings. About 50%, however, are single rings. But it also means that another 50% are multiple rings, and you can have up to 7, 8 rings. So like one case is AS209, for example. The number of rings is affected by resolution, because we know that, we learn from the history that our single rings, when you observe the disk at higher resolution, they tend to split up in 2 or 3. So the fact that there is a peak is not necessarily a physical result, but is more likely due to a resolution effect. The distribution of ring radii, these rings are found all over the place. Eventually, the disks are not that big, right? So generally, they have outer radii between 50, maybe 100 AU, and so you don't find ring very large separation. And also, in the inner part, okay, you are limited again by the resolution because you don't find rings very close to the star if you cannot resolve them. But for example, a very famous example of TW Hydra where we see a ring at 1 AU. So there is a broad range of location. So you can characterize ring with the location. You can fit the Gaussian profile. You can characterize ring with the width. And Zhaohuan will go in more detail about that. So let me move on because time is ticking. Spirals are less commonly found in disks. What I want to point out here is that spirals are common in binary systems. So that's something robust we have learned, and we'll go back to that. There seems to be a prominent peak at m equal 2, which is also a pretty robust result. So we tend to find m equal 2 spiral. And pitch angle tend to be large. And there is a tentative, perhaps, dependence of the pitch angle with the disk mass, and this is something that also Zhaohuan will touch upon. Lastly, before passing the microphone to Zhaohuan, crescent, we have, these are the rarest objects. There are 19 crescent, 13 disks. The occurrence rate is actually pretty large for the most massive disk. It's 30% for disks more massive than 5% of the solar mass. But it appears to be drop very sharply for low mass disks. However, crescent are not a well-defined class because we only define crescent, for example, we use the contrast. So you see a bright emission on one side of the disk, you see much lower emission on the other side at the same radius, and then you can measure a contrast. And we call crescent in our chapter only objects that have a contrast larger than 1.5. There are many rings that show azimuthal asymmetries that one might consider crescent. Another aspect that is important to connect the observation is the aspect ratio, because in some model that tells you about the physical origin. So with that said, this is kind of the observational summary, so I'm going to pass the microphone to Zhaohuan for the theory part.
So while we have structures in disks, structures reflect some basic properties of a rotating system. For example, if we go one step beyond a smooth disk, we could add rings and gaps. The radial pressure gradient could easily be compensated by varying the azimuthal velocity. If you allow the disk to be eccentric, we know eccentric orbit can be decomposed into a circular motion and a retrograde epicyclic motion. If the fluid has some coherent epicyclic motion, then you will produce you will produce a vortex and a large-scale symmetry. And the spirals is basically waves in the disks. If you perturb a static fluid like the surface of water pond, you have these spherical ripples. But if you perturb a Keplerian rotating disks, the perturbation will quickly be sheared into spirals. So all these features reflect just the disk existence of the disk. The more fundamental question is what drives these perturbations in disks. Since PP6, the number of theories to produce these spirals or these features also exploded. But overall, we could categorize them into 5 categories. You have hydrodynamic process, and then you could add magnetic field, one of the fundamental forces in nature, or you could invoke another fundamental forces like gravity, and the gravity could come from the disk itself, or it could come from external perturber. And since we observe the dust most of the time, you could invoke some dust, gas, multifluid physics inside. So I'll quickly go over all of these 5 categories and just highlighting where they will operate and what the features they will produce. Okay. So regarding hydrodynamics, the first instability is the vertical shear instability. So this instability allows the fluid to move up and down to tap some free energy from the system. And in order to allow the fluid to move up and down in the disk, you want to get rid of the buoyancy. So the disk needs to cool very fast. So this only happens at the outer disk beyond 10 AU. And these up and down motions will cause very narrow rings in the disks. And also these up and down motions could disturb particles up and down, leading to very thick dusty ring. So if you do 3D simulations, you could actually see vortexes forming by this instability. So at the inner disk, there are more instabilities, but generally they will produce vortices in disks. And then if you allow the background disk to have some structures, for example, if you allow the disk to have a ring structure, very, very sharp ring, you have very large velocity gradient across the ring. And this ring will become unstable and break up into vortices, and these vortices will merge. And there are several regions in the disk you could form these rings. For example, at the planet-induced gap edge, you could have a ring. Or you could have infall to some specific location, you will produce a ring. And finally, at the end of the disk evolution, photoaberration will become important, and they could also open cavity disks. Okay. So now if you invoke magnetic field, a very weak magnetic field can destabilize the disk. But in protoplanetary disk, the disk is poorly ionized. So in this case, non-ideal-Mechdy effect becomes very important. But even with non-ideal-Mechdy effects, the magnetic field could self-organize itself to form structures. For example, here we have a disk, smooth disks with a constant amplitude diffusion coefficient, but the magnetic field organizes itself and break the disk into many rings. On the other hand, these rings are not very strong, so they cannot form vortices, and normally they don't produce spirals. Because the non-ideal-Mechdy effect is determined by the disk ionization, is affected by the disk ionization. And in protoplanetary disks, the ionization varies dramatically from inside to outside. So at some transitions where your ionization changes dramatically, you could pile up mass and form like rings or even vortices in disks. So now, after magnetic field, we could invoke gravity. When the disk is massive enough, that normally happens for early system, or at the outer part of the disk where the temperature is low, then you could have graphene instability produce these spirals. So the main feature for the graphene instability is the spiral. And generally, when the disk mass increases, the spiral opens up, and also the number of spirals decreases. Eventually, you will have number 2, m equals 2 spiral, but with very massive disks. And these spirals are very transient. So they come and go, and they orbit around the central star at the local Keplerian speed. That also means if you have dust that orbit around the star at Keplerian speed, they have a lot of time to interact with the spiral, So these spirals could concentrate dust particles, and then they can be observable by ARMA. And these spirals will perturb the disks, and we should be able to detect some kinematic features of these spirals in the future. So if the gravity comes from perturbers, then we could have planets in these disks, and this is most well-studied case. And the planet will excite these spirals, and these spirals could open gaps, and the gap edge could be unstable, form vortices, and trap dust particles. So the planet is very convenient to produce all these disk features. On the other hand, these spirals co-rotate with the planet. So the particles do not have a lot of time to interact with the spirals. They will move in the spiral, move out of the spiral. So these spirals cannot trap dust particles very efficiently. And because the planet is highly embedded in the disk, so the 3D effect or thermodynamics actually becomes very important. And the planet's history is also important for the rings and vortices in disks. The perturber does not have to be bound to the system. You could have a flyby event, and this flyby event will excite spirals at the closest approach. But these spirals will be transient. Okay? After the flyby, the spirals will disappear after the sound crossing time. Okay? So you could also have the perturbers inside the disk, inside the cavity. So this is the binary disks. You have a binary star at the center. The binary star will perturb the disk, produce all these features. And then you will generate this lump at the inner cavity edge. And this lump is very similar to vortex. It has large aspect ratio. It co-rotates at a local frequency, and they can trap dust particles. But there are some differences, like they are very dynamical. There is no vorticity minimum. The binaries does not have to be coplanar with the disk. This is one of the recent discoveries, that the binary plane and the disk plane could perpendicular to each other as long as the binary has eccentricity. So you could have these polar aligned disks, also with spiral, cavity, and vortex. And more importantly, we have observed some of these systems. Okay. So finally, the dust processes. Dust will settle in the disks and produce streaming stability. On the other hand, this streaming stability produce very narrow rings and gaps, which are not observable with ARMA. But future, we need these bigger simulations to see whether these structures could self-consistently merge into larger structures. And we also have other dust-related instabilities, but generally they produce rings in the disks. And if you have a lot of dust concentration in the disks, they can produce gas rings. And finally, the dust could sublimate at particular radii, the dust sublimation radii or ice lines. The physics around the ice line is very complicated, but most of the models predict that you could have rings very close to the ice line. Okay. So this is all of the theories, and now we try to make any connection, or whether we can find any connection between these observations. The such comparison is very difficult because most of the simulations include gas only, while most observations trace the dust particles. So some proper interpretation requires some understanding of the dust and gas interaction. But we will proceed. So for the rings and the gaps, since the perturber so far is the only confirmed mechanism, we have the system, for example, PDS-70, we have 2 planets in the system, and these 2 planets induce gaps. And the planet scenario is very versatile. You can put a planet anywhere, so produce rings anywhere with any width and any depth. And also a low mass planet could produce rings due to particle trapping. So if we assume that all the rings have planets, we could actually use the population of the ring and gaps to generate a young planet population in disks. And we could probe very low mass planets. But the caveat is that this planet mass determination is very uncertain. It depends on the disk properties and the dust properties. And the planet needs to be within the dusty disk in order to be detected. And of course, another bigger question is whether all the rings could harbor planets. So could the rings be induced by the ice line? Current observations seems to not support these mechanisms. If you look at all the rings, they kind of everywhere. They do not actually coincide with these predicted ice lines. But there are, in some cases, you do find some good correlation between the ice line and the dust rings. Okay. So, okay, so about hydrodynamic and magnetohydrodynamic process, we don't have any definite test yet. We need more diagnostics. For example, for hydrodynamic process, we need velocity signatures. For MHD process, we need to detect magnetic field. For the dead zone edge, we need to detect some ionization transition in the disks. And finally, for photoaberration or MHD wind, we need to detect wind directly, which associated with these gaps and rings. So about the spirals, so far, again, the only confirmed mechanism for spiral is the companion, is the perturber. In this system, we have a companion here inside these two beautiful spiral. And for the HD10456, we have a companion, have these two spiral, and will reproduce by numerical simulations. So you could argue that all of the spirals are associated with the companion. But we didn't detect them because they are very faint. Maybe they are produced by the planet, but the planet may be faint since it could have a cold start, or the planet could have variability, or you could have circumplanetary material to block the light. So this is one possibility. Another one of the favorite possibilities is the gravitational instability. On the other hand, our data, clear data, seems to not support this, at least not for all the systems. If most of the spirals, if all these M-equal spirals are due to gravitational instability, these should be relatively massive. But we don't find any correlation between the number of spirals with the disk mass. And there is this correlation between the pitch angle, the openness of a spiral, with the disk mass. This is opposite from what you expect from gravitational instability. You would expect with a higher disk mass, the spiral will open up. But the opposite seems to be the case. And finally, we see the spirals at any disk radii. It's not preferable at outer disks. So on the other hand, we see some of the, as we heard before, there's the info kind of produce this M=1 spiral. So in future, it's important to see whether these features connected with any of the features inside the disks. So now we move into the crescents. Again, for crescents, the only confirmed mechanism so far is by perturber. For this system, HD14257, we have binary at the center, and these two binaries could produce these spirals and this crescent structure. So one outstanding question for the crescents is that are all these crescents correspond to vortices in disks? And so far, it seems the properties of crescents are consistent with those predicted by vortices. For example, all the aspect ratio of the mirrored crescents is larger than 3, consistent with stable vortex configuration. And the contrast of these crescents are very high, can reach to larger than 10, also consistent with the picture that particle trapping is happening in vortex. And the aspect ratio, there is a tentative trend that aspect ratio will increases with the disk mass. This is also consistent with the vortex theory. In more massive disks, the vortex will be more elongated. Okay. But the definite test for this vortex explanation for this large-scale crescent structure is by measuring the kinematics. So we really need to measure the retrograde motion of the gas fluid, but this requires us to have very high-resolution observations in future at the same spatial scales and the dust continuum observation. This is some previous attempts, but you could see that it suffers this beam smearing with two large beams. So in the end, for the future perspective for theory, we need a better theory, of course. We need more realistic physical model. It has two meanings. The first is we need more complete physics. All these physical processes, radiation, dust, magnetic field, and chemistry are intertwined together. Your radiation affects your chemistry chemistry affects your ability to couple with the magnetic field, and your dust affects your chemistry, so we need to have this more complete physics. And also we need to simulate from large scales to small scales. And another meaning for more complete more realistic physical model is that we need build models specifically for particular sources. So far, as theorists, we have not taken full advantage of all the observational constraints. We start with the simple disks, but we actually have more information. For example, we know the disk surface density from CO observation. We know the 3D temperature from these molecular tracers. And we know the dust size distribution from some millimeter continuum observation. So we need to incorporate all of these observational constraints into our theoretical model or MHD simulation or whatever simulations we will do. So hopefully, with all this detailed modeling, we will be able to compare with observations and answer this question: are these structures due to planet, or they are actually precursors of the planet? I'll handle this to you.
Yeah, so if theory needs more work, we need more work on the observational side for sure as well. Again, this is a pretty recent field, and so you cannot expect that we are done already. But, so we're trying to, so I want to touch on 3 main points here that we could do better in terms of observation. First of all, we need, as I said, we need to observe this fainter disk. And we want to understand if the substructure are ubiquitous or if there is a trend with stellar mass, for example, or disk mass. For example, you expect gravitational instability in massive disk. If we start to see structure in very low mass disk, we can rule out that tool. And so we still cannot do that because we have this problem that we are only observing the most massive, largest disk. We need to observe younger disk. And we have beautiful surveys that are going on, like E-disk, that they focus on class 0, class 1. We want to know where these substructure form. We want to know if the substructure are intrinsic to the disk formation or not. We are assuming that disk forms move, and then you need some physical process to create substructure. But maybe disk form with substructure from the very beginning, and that's touched to the fact that we need models that go from envelope to accretion to the formation of accretion disks. And again, so the E-disk problem is showing beautiful observation. So there is much more work to be done with ALMA. The caveat here is that, particularly when you go to this young object, the optical depth may become a major challenge because this class 0 object might be optically thick at millimeter wavelength. Class 2 disks, these massive class 2 disks are already partially optically thick. So we need to go to longer wavelength to beat down the continuum opacity. So SKEA and NGVLA will play a major role in the next probably 20 years. Gas emission. So we need to observe gas emission at very high angular resolution. This is really challenging, even for ALMA. It can be done. It just takes a lot of time. So the challenge is convince the panel to give you enough time to spend to achieve this very high sensitivity. But if we want to understand, disentangle these physical processes, for example, we need to be able to measure gas velocity, not only tangential gas velocity, we need to be able to measure radial gas velocity and vertical gas velocity, which are a smaller fraction of the Keplerian velocity. So we need high angular and high spectral resolution, which is really pushing the capabilities of ALMA. Again, the caveat here is that, as also Claudio mentioned before, continuum can kill your lines because if everything is optically thick, all the photons are the same. You don't care about whether they are from line emission or not. So we need to go to longer wavelength, like ALMA band 1 and band 3, and here you lose angular sensitivity. So again, it becomes challenging, but it's not impossible. And the future telescope like NGVLA, where you can do observation like ALMA in band 3, but at 10 times better angular resolution sensitivity will be really key to expand this field. Last but not least, planets. We all like planets. And we predicted many planets, but are these planets, do they really exist or not? I think is a big question. We have a few. PDS 70 is a very robust detection. There are a few others that are candidates, but we need more. JWST can detect some of these, at least the ones that are farther out enough that your contrast is low enough, you can achieve low contrast. So I'm looking forward for the JWST section to see if there will be something about exoplanet. With that said, so these are our conclusions. I hope we convince you that there has been a huge amount of progresses, both in terms of observation and theory, since Protostars and Planet 6. Thanks to ALMA, thanks to near-infrared high contrast imager. It's not only ALMA. Are substructure ubiquitous? Yes, at least in the most massive disk. The question is pending for the less massive disk, where we need higher angular resolution observation. Do the occurrence and morphology of these subtraction constraint formation processes? I think you have learned that theory is complicated, maybe. Gravitational perturbation by companion definitely play a major role. We see this beautiful spiral in binary system. We see these beautiful rings in PDS-70 system. However, these physical processes are not mutually exclusive, and you can have multiple processes that are they are at play at the same time. And then, I mean, again, what is the connection within substructure? I mean, there is at least one robust detection that we have a strong connection. But, you know, one is clearly not enough to derive any strong conclusion. So with that, I'll stop. We will be happy to answer any questions.
Thank you very much for excellent talks. And now the floor is open for questions. Okay, let's start with this line.
Hi, Gijs Mulders, University Adolfo Ibáñez in Chile. I was wondering, you mentioned going to resolve the structures closer to the star as well. Is ALMA going to get us to like the 1 to 10 AU range where we detect most of the giant exoplanets?
Yes, it can be done. It just, it's challenging. It takes time, and as everybody that works with ALMA knows, if you want to do high frequency observation, despite the fact that ALMA is 5,000 meter elevation, the good weather for high frequency is not that abundant. But it can be done with enough time and enough telescope time, for sure.
Okay, let's have a question from the other side.
Peter Woidke, Graz in Austria. I have a comment about the disk mass because the formula you showed, the traditional way to derive the disk mass, is of course not very precise. And you didn't mention really all the uncertainties that go into this. I mean, you mentioned that the disk can be optically thick, that's one point. But in disk models, what we do is we see that sometimes the dust is so cold that it's actually not even emitting in the Rayleigh limit. That's another big effect. And then, of course, you have the opacity uncertainties, and you have the 0.01 factor. I think you also didn't mention it. I just wanted to know all these nice attempts to correlate now the observations with the disk mass hinge on our ability to pin down the disk mass. And I think this is still, when you look at TW Hydra, for example, there's still, I mean, this is the best observed system maybe, and still there's a large uncertainty about the disk mass. I wanted to invite you to comment on that.
Yes, I completely agree, and so I didn't have time to touch on that because time is limited and we want to cover a lot of things. But yes, I mean, clearly there are all the uncertainty that you mentioned and more. We don't know well the dust opacity, and we don't know the dust to gas ratio and so forth. So I think, measuring disk masses is still one of the main challenge. And we have now some new technique, for example, doing dynamical mass estimate using ALMA, and there are more results that will become soon. But to some extent, for the structure, the mass is important. The radius is also important as well because it's more like a resolution argument. But I cannot just agree with you. There are a lot of uncertainties.
Okay, let's have a question from the back.
Ilse Cleaves, University of Virginia, thank you for this very nice talk. On your 50% of disks that are single-ringed substructures, are these what we used to call transition disks? And on a related note, are these bright ringed systems, are they always singles? Do we ever see small-scale substructure when there is a single bright ring? And I guess from the theoretical perspective, is that interesting?
Okay. So observationally, not all the single rings are transitional disks. If we go back to the very first slide, I mean, one clear example is very famous one is LK 15. That yes, it was a single disk. It was a single disk observed at 0.2 arc-second resolution. Now it's made of 3 rings, for example. So I think most of the single rings tend to be disks that have been observed at relatively low angular resolution. If I have to guess, I would bet that all these single rings are multiple rings.
Okay, let's have a question from this line.
So
just sorry.
Comments on the theory part. If we could see the rings break up into more pieces at longer wavelength, that would be actually more important or more interesting. because theoretically, you would expect a lot of these rings have sub-structure, eventually want to form planets. So observing, make sure that these rings are really axisymmetrical, or quantify the azimuthal contrast within the ring will be very important for theory.
Yeah, go ahead.
Yeah, so Doug Johnstone, National Research Council of Canada. That's a very nice talk, and I have a comment and a question. The comment, really quick, is just to say that as you go to younger disks and as we observe them deeper and we have longer observations of the variability, it'll be really good to tie these two things together. So that's perhaps a chapter for Protostars and Planets 8. But the question is, related to that, in your GI, you were getting a lot of, you were getting multiple arms on your rings, and you were having, I thought you said it dissipate very quickly. Was it actually spreading? Was it dumping material into the center? How was it re-equilibrating, and is that because you aren't allowing it to continue to accrete mass?
So the spirals, so two mechanisms, one is self-gravitating spirals. Those spirals could last very long because they are transient, they come and go. They will transport mass from larger radii to inner radii. But they will eventually stop where your disk become very stable. You cannot shovel small mass all the way to the central star.
So the people who do gravitationally unstable disks that get all the way to fragmenting, how do they do that? Do they need to be dumping mass on at such a quick rate? Is there a threshold where you go from being able to smoothly to clump?
Yeah, so in order for fragment, normally people think the disk needs to cool fast enough. So it's tied back to like opacity and the ability of these to cool. If you cannot cool it enough, you form spiral, but the spiral will not collapse. They will maintain a spiral. So it goes back to the thermodynamics of the disk. Normally that happens at outer disk where it cools fast, so you could form these clumps.
Excellent, thank you.
Yeah, there are many questions, so we extend our question time a little bit. Okay, let's have a question from the other side.
Okay, thank you. Hiro Takami from Asia. My question is, do disk structures seen at the millimeter and optical match in general? What is the current observational view, and what are theoretical predictions? Not just a few specific cases, in general.
Well, in general, I cannot answer because we don't have a general picture. I can talk about few specific cases, unfortunately. Sometimes they do, sometimes they don't. MWC 758, shown here, it shows spiral in scattered light. You also see the same spiral in CO emission and in dust in millimeter continuum. So they match. You see also crescent in millimeter continuum and infrared. So in this case, they do. In this case, they don't. You see a lot of crescent in millimeter continuum, but you see a lot of spiral in infrared. Spiral trace micron-sized particles. These are those that scatter your infrared light. Millimeter trace sub-millimeter grains. So either this is due to a different distribution, you're also tracing different layers. So it's very hard to connect different layers and different particle distribution because there is gas-dust dynamics. So unfortunately, I cannot give you a general picture. I think we need to, unfortunately, we need more observation.
Thank you. And any theoretical predictions? Any comments from Zhaohuan? Thanks.
So theory-wise, that means the disk surface and disk midplane are very different. So that means we really need to look at a lot of 3D effect. That also opens the possibility to test a lot of theory. For example, the spirals could be opened up at the surface because the sound speed is higher at the surface. So if we could carefully compare these with a detailed model, in which case your model do consider these thermal stratification, then we will have a better comparison between simulation and observation. Current simulation is very simple. Locally isothermal for most of these is, so they are not capable of distinguish mechanisms.
Thank you.
Okay, question from the back.
Hi, Francesco Lovascio from CRAL at ENS Lyon. So we've been hearing a lot about particle size distributions. There is an offhand mention in the talk that now we can sort of constrain it, and then we were talking about now, well, that we're capturing physics of different particle sizes. So I have sort of two connected questions. The first being, how well can we actually constrain the dust size distribution? And the second being, do we now have to run polydispersed simulations of everything, which are a nightmare?
Okay, I'll answer about how well we constrain the grain size distribution. Well, probably the best thing to do is go back to Protostar and Planet 6 and to look at the chapter about that. And the state of affair didn't change much. One thing that happened in the last, meaning that we use the spectral slope of the millimeter emission, and then from there we constrain the spectral slope of the dust continuum emission, the dust opacity, but it's degenerate with optical depth. And in the past, we tend to believe disks were optically thin, so that the connection between spectral index and dust grain size was pretty well understood. Unfortunately, what ALMA observations show is that most of these rings are actually optically thick. And when they are optically thick, then there are two things. One is that you lose the dust opacity slope. The other is that scattering a millimeter wavelength might be important. And if scattering is important, what you find is that essentially you cannot constrain. You can only put a lower limit on your grain size, which is relatively small. So in most of these disks, say you need to have probably 100 micron size grain, but maybe there are millimeter grains or centimeter grains. It's very hard to tell. So it's a very complicated problem, and it unfortunately became more complicated in the last few years due to the fact that these disks are more optically fit than what we thought. Theory-wise, one thing I want to say is that, yes, we are already doing multi-fluid simulation where you have multiple dust grain and multiple and gas together. It's not making the comparison with the observation any easier, unfortunately, because now you have many, many parameters that you need to explore.
Okay, let's have a question from this line again.
Kate Follett, Amherst College. Thanks, Andrea and Zhaohuan, for a really clear and compelling talk and chapter. Really exciting stuff. I have two questions. Hopefully, they're kind of quickish ones. One is, so when we're doing observations of these structures in scattered light and in continuum, millimeter continuum, what are the qualities of the morphological features that are going to probe the formation processes for them, or the things that incite them? So, for example, I know the width of the rings, it sounds like, is important, the pitch angle of the spiral arms, the extent of the crescent structures, but sort of related to that, how do we quantify those? It strikes me that a lot of them are kind of sensitive to what our resolution is. So how did you guys in the chapter identify features? Was it kind of qualitative or quantitative? And I had another question, which was just for the flocculent spiral arms, are there any good models for what creates those as opposed to sort of a classical grand design two-arm spiral?
Yeah, regarding the first question, in the chapter we try to measure as many measurable structures as possible, like the ring width for vortex, the vortex aspect ratio, contrast, spiral is the pitch angle, number of spirals. So these are all the information you could extract from the observation. Of course, the more the better, but that's all we tried. With this limited information, we could still start to compare with the simulations or theory from a population point of view, not a single source, but from a population point of view. Regarding the spirals, in a lot of simulation, you could see the spirals are not actually grand design. Like the these spirals will vary in the disks, so they could generate additional spirals. So those ones are very hard to compare with the observation, because whenever things get chaotic or like very random appearing in the simulation, it's very hard to compare with the observation. Yeah. So we need to pick some big features to be compared.
Okay, the next question from the other side.
Hi, Nagayo Hashi from Taiwan. Thank you for the very nice talk and also mentioning about the e-disk survey. So I have a question about the time scale to create those substructures. Because based on the e-disk survey, we see the less distinctive substructures in earlier, younger disks. So that could mean that the substructures could form relatively quickly when the protostars evolve to the class 2 type of stars. So I'm just wondering whether you have any comment on that.
Most theoretical works focus on the structures which form very quickly, because that is we do simulation. We don't want to wait a long time to see structure. But there do have the like circular gravitational stability, which takes longer at the circular time scale. So all the structures you see happens relatively within 100 orbits. So that is at 100 AU, that's around 10 to 50 years. So it's kind of okay. Yeah.
Okay, thank you.
Let's have a question from the back, in the middle.
Hanpu Liu, Peking University. This is a question connecting this talk to the first talk this morning. So how can, in the first talk this morning, we talked about accretion variability. So I was wondering how can substructure of protoplanetary disks help us understand more on accretion variability? So is there any theoretical prediction or observational hints? Thank you.
A lot of accretion variability measured in English talk is from the inner disks. Those are the accretion onto the star. While AMA is observing the structures at much larger scale. But that's an interesting question or connection, because the inner disk could, for example, we will hear, cause shadow to the outer disks. So by studying these correlations at different wavelengths, at different scale, it will be important to constrain the disk structure.
Yeah, I want to add that, for some object, for example, FU Orionis object, clearly if you have a strong outburst that increase the luminosity of the central object by order of magnitude, then the temperature of the disk also increases. It should respond to that. And so in processes like snowline, you expect your snowline to move, and there are results that suggest that we see this ring very farther out because in some of FU Orionis objects due to this effect. So there are connections. I think currently, there are not many results, and as Zhaohuan says, it's hard to connect the very innermost region to these tens of astronomical units, but there are interesting connections.
Thank you.
Okay, have a question here.
Thanks for the interesting talks. I'm Ken Chen from University College London. I see from the talk there is a currency rate comparison with the disk properties and like the locations in the disk. I wonder, is there any occurrence rate has a relation with disk time, disk age, for example, like any time evolution between those substructures? So for example, if I run a simulation, I usually, if I want to build up a substructure, I usually maybe just run the simulation to certain orbits, or maybe reaching the so-called quasi-steady state, or maybe if you have a specific disk to study, you run the simulation to match the disk lifetime. But is there any like time evolution for those substructures you run different time for your simulation? You may see different things.
I don't think we can claim that there is any robust dependence with age. Stellar ages are very difficult to constrain, particularly for these kind of relatively massive star. So, we only know the ages of the region that this star belongs to with uncertainty of millions of years. So, it's very hard to do that. One way to constrain, ages in general term is connecting, for example, class 0 object, class 1. And so that's why in our conclusion, we say, we need to observe this younger disk. To address the previous question also, there is a caveat with the optical depth. So the fact we don't see structure in class 1 object at 1 millimeter doesn't necessarily surprise me, because this disk also show evidence to be optically thick. And so this makes, unfortunately, looking for this structure in this young disk that will help you to constrain ages is even more difficult.
Thanks.
Yeah, we will have only 2 more questions. So one from this side and the final one, this one.
Okay, Scott Wolk, Center for Astrophysics. This is related to the other 2 questions. When I look at the D-sharp data, or I've seen pictures of the D-sharp data, they show as a function of wavelength, the images change dramatically. And so my question is, do you actually see as you change the frequencies, in the ALMA data, do you see structures transition from one to the other, from spirals to crescents or something like that?
No, I don't think we see that. We see, for example, in rings, as you go to longer wavelength, they tend to become narrower. And this is explained or understood in terms of concentration of dust particles, so dust trapping, where largest particles are concentrated in a narrower region. But maybe here in the audience someone can correct me. I don't think we have evidence of going from one structure to the other, at least in the wavelength covered by ALMA and VLA. When you include infrared, yes.
Thank you.
Hi, I'm Shoji Mori, Tohoku University, Japan. Thank you for the nice talk. I'm curious about the statistics of the observed mass ratio between the disk mass and sphere mass. And actually, I never saw that the disk without this one. Yeah, disk without substructure showed lower the mass ratio, but actually it's opposite. But so I'm curious, but can we interpret it as a just observational effect? I mean, that's lower angular resolution, or any other theoretical prescription, speculation for that?
Yeah, so the fainter disks, so if you look at the mass ratio, is this diagonal line are mass ratios, so disk with equal mass ratio. Okay, so this is 10 to the minus 1, 10 to the minus 2, so this is kind of your minimum mass solar nebula, 10 to the minus 3. And the disk structure tend to clamp here, but the point is that as you go to this fainter disk, we don't resolve them. So it's an angular resolution and sensitivity problem. And so it becomes very incomplete. When we say with no structure, it means that we don't see structure. It doesn't mean that there are no structures. Mm-hmm. And so the point is we need to push the observation down to this regime so that we can tell whether there are structures or not.
Okay, thank you.
Okay, then thank our speakers again.